This video is to show how to use lip bridge concrete to design a typical simple span bridge. And today's example has a simple span bridge with span length equals to 100 feet, and the bridge width is 52 feet. And this bridge uses AASHTO standard I girders with 6 girder lines and 9 foot spacing. The overhang equals to 3.5 feet. Deck thickness 8 inches. And deck use HBP deck overlay, 36 pounds per square foot. Stay in place deck form, 8 pounds per square foot. Utilities, 5 pounds per square foot. And this bridge also have median 4 feet wide and 9 inches thick. And this bridge use steel railing with 1.5 feet and 100 pounds per linear foot each side. The live load on this bridge use HL93 live load. For the concrete strength, 1 day initial strength equals to 6 KSI, and 28 days final strength equals to 8.5 KSI. And for the pre-stressing strength, we are going to use 0.6 inches diameter, 270 KSI low relaxation strength. For the intermediate diaphragm, we are going to use the spacing 20 feet and the size use W shape 24 by 76. After you open the lip bridge concrete software and this window pop up, and since we just designed the superstructure for the pre-stressing concrete girders, we are going to directly to superstructure. After that, this bridge is precast pre-stressed girders and choose that option. So for the project information, we are going to put some basic project information like project name. I will put this as 100 feet simple span. And for the job number, I put the course number. And state, I put New York here. And your name. Okay. And some descriptions about the project, just put some basic information for this bridge design. So I will put a simple span, 100 feet, bridge width, 52 feet, 6 girder lines, at 9 foot spacing, overhang equals 3.5 feet, deck 8 inches, and future wearing equals to 36 plus 5 utility, so equals to 41 pounds per square foot. Steel railing, 100 pounds per linear foot each side. And we also have the median. Equals to, based on the calculation, 4 feet wide and 9 inches thick concrete. We are going to have this 0.45 kg per linear foot for composite load. Okay. So after some basic information about the project. Now let's go down to the page, okay, to choose the code. We just use the default latest code LRFD8. And for this example, we don't have any state specification applied. And for unit, US unit. And we have the constant girder spacing parallel, so not flared girders. And for the span type, choose simple span. Now going to the geometry. Okay, so when you do the modeling, save your file frequently, just in case the program have unexpected crash. So for example, I just save as 100-foot simple span. AASHTO Girder. Okay. Okay, so now let's do the geometry. For the overall width, we have 52 feet. And for this bridge, it's no skew. It is a orthogonal bridge. Okay. For curve data, that's the railing or barrier. So we have 1.5 feet and 1.5 feet on each side. And for the line data, after you input the bridge width and the curve data, like the bridge railings, and this program will automatically calculate the number of design lanes with the regular design lane with 12 feet. Okay. So go down to the topping data. We have the effective deck thickness is 8 inches, and this represents the structural depth. And deck thickness represent the concrete portion that's sacrificial, serve as a wearing surface. And for this example, we don't have any sacrificial concrete depths, so just leave at 0. And haunch thickness, and we'll put this 1 inch as a minimum because this topping data are using to calculate the moment inertia to contribute the girder strength as well as the stiffness. So for here, the input, we want to be conservative for the structural capacity. So for haunch, we just put 1 inch minimum. And we assume the average haunch thickness is 3 inches, usually in design. And we will input the 2 additional haunch thickness as an additional load in the load step tab. Okay, so we're going to input the additional haunch thickness in the loads. Okay, and after that, haunch width, we will do the auto set haunch width. After you choose that, whenever you choose a girder size, and this haunch width automatically set as the same width as the top flange width. Okay, and for span data, and this bridge precast length, that represents the total length of the girder that you produced in the plant and is bigger than the span length. Span length is center to center bearing, and precast length is total length of the girder. And on each side, beyond the centerline bearing, and usually we put 9 inches additional beyond the center bearing in order to accommodate the bearing pad. So based on that, we have 100 foot plus 9 inches on each side times 2. So we end up get 101.5 feet for the total length. And for the release span, same as the precast length, okay, for this problem. And the bearing to bearing represents the span length, which is 100. Okay, and after you input, and you do see the section show up on the screen, and for you to check the geometry input. And go down, okay, go down to the beam type and location. And for beam number 1, and beam ID, and in this whole beam section libraries, a lot of um, the girder sections already in this library. Okay? And for us, and we will pick AASHTO standard I-beam. So it's already in this library. We don't need to create a new section. So let's take a look at the girder size selection. Okay, based on the span to depth ratio. Okay, so based on span to depth ratio, and usually that's the first step that we determine the girder size. And for the concrete, prestressed concrete depths, we use the span length times 0.045 to get approximate depths of the girder. Then we can pick a girder size based on this approximate depths. Okay, and according to this ratio, we have 0.045 times 100 foot, that's span length, get 4.5 feet. And so this gives you 54 inches. After that, go to this New York State, this pre-stressed concrete girder details, and we will refer to those standard size. And for the AASHTO I girders, we will refer to the bottom row here. Okay, the top row is PCEF. Okay, so today we focused on the AASHTO. And according to 4.5 feet or 54 inches, we find that type 4 is your selection. Okay, so this type 4, the depth is 4.5 feet. And this match what we just calculated. Okay, so just calculated approximate depth and match that very well. And we end up, okay, so try the type 4 beam in this example. Okay. So for pre-stressed concrete girder, we determine the size is based on span to depth ratio. And after that, we pick a girder size match the depth. Okay, so this is AASHTO type 4. So from beam ID, we get AASHTO type 4. And you see this type 4 girders is shown on the screen. And the distance for the first girder, and this dimension is overhand 3.5. Okay. After that, we just highlight this row and do copy row and change the distance from last beam to the beam spacing 9 feet. Okay, and you do see this the beam spacing here. After that, we just keep doing copy row 4 times and finish the whole framing. And you can see the girder location in this screen to check your input. Okay. So at this point, we are done with geometry and move to the materials tab. And material tab start with concrete and concrete weight. We just have the normal weight concrete. So those 150 is good. And for the girder release strength, according to the given information in this problem, and we do have this 6 KSI as initial, which is as a release, and final strength 8.5. So we use those input. The initial is 6, and the final is 8.5. So after you input those, you will see the elasticity, which is Young's modulus, change accordingly. So you don't need to do your input. The program will automatically calculate that based on the AASHTO equations. And for the deck concrete, 4.5 is the common used concrete strength for the cast in place deck. So we just leave this as 4.5 KSI. And Poisson's ratio, thermal coefficient, those are standard numbers, and we don't change that. And for the tension bars, we have the elasticity, Young's modulus, 29,000 KSI, and grade 60 still represents the yield strength is 60 KSI. Okay. So go down to the transformation steel, and this portion is used the steel contribution to the moment inertia and and as well as the concrete strength. So for this portion, at beginning of the design, I will leave those just as is, just leave this blank because that I want my initial design be conservative. And if I find that the moment inertia need to be increased a little based on the live load deflection at the end of the design stage, I know this is the place that I can increase the moment inertia by some degree. So this gives me some room to increase the stiffness to the girder. But for initial design, we just keep those empty. Okay, so to keep those empty. But we understand this part give us some room to improve the moment inertia. Okay, so go to the pre-stressing tendon. And for this example, we are going to use, for this particular example here, we have 0.6 inches, 270 KSI, low relaxation strength is right here. So according to the given information, we are going to choose the corresponding one. So this is 6/10. So this give you for each strand diameter 0.6 inches, and 270 K represents the ultimate strength of the strand, and LL represents low relaxation. Highlight that. And for the pattern, so we are going to use stripped and straight and this combination, and this also show in the New York State standard this girder detail. And if you just go down to the pages in this detail, you will see that for AASHTO girder right here, and we do have the harped strand. So this harped strand as well as the straight strand. So those are straight strand locations, and those are harped strand locations at end. And this the harped strand location in the middle of girder and straight strand in the middle of girder. Okay, so it's a combination of dripped strand and straight strand, which is default in the program. And the remaining here, depress point fraction 0.4, and this also match the New York State standard girder details, and see that this dripping point right here start to bend the bar, bend the strand. So the middle portion is 0.2 times the entire length, or the beam length, okay, the entire beam length. And then the remaining to the end of the girder, use 1 minus 0.2 divided by 2. So it's 0.4, okay? Okay, so mid-span increment, that represents the strand spacing. Okay, the strand spacing, 2 inches, that's standard. And for the remaining data, those are default value, match the girder detail pretty well, so we don't change those. Down with the material. So now we go to the loading. Before we do any of the hand input, we'll use, okay, so for permanent load, which represents the dead load, and we'll use the wizard, okay. And this window pop up for wizard. So we put this left barrier weight, so that's reeling, okay, so 0.1 key per linear foot, that represents 100 pound per linear foot. And the red barrier also 100 pound per per linear foot. That's 0.1 key per linear foot. So we don't have additional curve data. Here, just leave those blank. And future wearing surface, that's the HBP deck overlay plus 5 pounds per square foot of utilities. So total 41 pounds per square foot. So we have 0.041 key per linear foot. Okay. So for stay in place deck form, instead of input here, I will input just manually in the permanent load table. So I don't do this as a wizard. So in this wizard, basically I input the barrier weight, future wearing, as well as the red barrier. Okay, just click OK. So after that, I do need to do some additional input for the dead load. Okay. So first, let's follow the sequence here. Okay, for the load, the deck weight already automatically calculate covered by the program. Okay, after input the deck thickness, and the program can calculate the weight for that. Deck overlay covered by the future varying. Okay, so now it's deck form. Okay, deck form. And we have the deck form for the interior girders use the 8 pound per square foot times 9 foot, which is tributary width. Okay, so we end up like 0.072 key per linear foot. And for the exterior girder, so we basically have the half, okay, it's half of the span length and plus overhang, but overhang is usually the wooden force work for the overhang portion. It's not permanent load. It's a temporary force work. So we have half of the weight as interior girder, so we get 0.036. So we input those numbers in the deep bridge concrete. And first span number 1, so we only have one span for this example because it's simple span. And beam number 1, precast DC, that's stay in place deck form. And here the loading type is line load. The magnitude is 0.036 for exterior girder. And I put some description here. It's called stay in place deck form. And then I do the copy row. Okay, so highlight this one, copy row, and then change that to girder number 2, and line load again, but the magnitude update to 0.072. Okay, so also stay in deck form. So keep copy row and change to 3, and copy row to 4, and copy row to 5. And again, copy row to 6, which is the exterior girder. And for this one, we get 0.036, okay, for the exterior girder. Okay. So after that, we cover the stay in place deck form. Let's take a look at the original one. So we cover that. Utility covered by the future varying. So now it's a median. Okay, so now it's a median. And we have the 0.45. Okay. Key per linear foot. This is a composite load. So move the arrow here, say insert row. And we do have the composite load for median, which is a line load. Put 0.045 key per linear foot. And this, I put this median, okay, weight. So cover that. This steel railing is covered by the wizard. Okay, so we input that already. In addition to all of those listed, and we do have the haunch, okay, because we input 1 inch as a structural depth. And now we do need to account for the 2 inches additional haunch thickness based on the concrete, based on the concrete density as well as the top flange width for the type 4 girder, the AASHTO type 4 girder, 20 inches and 2 inches thickness, and we end up at 0.042 cubic linear foot. And 20 inches top flange, and this one is from the New York State girder details. And if you take a look at this girder details right here, it's 1 foot 8 inches that represents 20 inches. Okay. So put your arrow here and in the row and just girder number 1, precast DC and line load 0.042. Okay. So I just put the description 2 inches additional haunch. Okay. So this haunch is actually on each girder lines. So I just do the copy row and change the beam number to 2, to 3, and keep copy it to all 6 girders. Okay. So at this point, down with the permanent load, which represents all the dead load. Now move down to the diaphragm. So this diaphragm used to laterally support the entire girder line to prevent lateral torsional buckling. And if we take a look at the girder details, and those either a cross frame shape or a diaphragm that's laterally support the girder lines. Okay, so for our example, we do have this intermediate diaphragm spacing 20 feet and use the W shape 24 by 76. And if you refer to the girder details, for the diaphragm, okay, so right here, for the diaphragm, I just make this a little bit bigger. For the AASHTO I-beams, we have a type of 4 right here. So the minimum recommended size is 24 by 76, and we try that. Right here. Okay, so give that a shot. Okay, so after that, back to this program diaphragm, and we'll use wizard. Okay, so this window pop up, and we can do like span number 1, simple span, location 0, and you see that the 0 represents at the abutment, right? And the magnitude, W24 by 76, and 76 is a pound per linear foot. No skew for this example, okay? So we do, then we do the copy row and change the location to 20, so every 20 feet, and do copy row and change the location to 40. And you do see on the screen, those locations show up, and for you to check your input. And the copy row again to 60 and 80. Okay, and finally is 100 represents the right abutment location for diaphragm. Okay, so those are the locations of diaphragm showing on the screen. So we just click OK. Then it automatically calculate the diaphragm weight on the girder lines as a point load. Okay, So move to this live load portion. Okay, so we don't check this option for now. And for temperature thermal load, we would use currently we use uniform load for typical girder. And for design live load, since this has no sidewalk, we don't add the pedestrian load, but we do need to include the live load deflection for the analysis. Okay, so let's go down to um, the design track, design lane load and so on. And this just gives you some of those live load in the live load library. And for the HL93 live load, we have the defaulted already selected in this deep bridge concrete software. So if you design a bridge just has HL93 live load, there's no additional input. So this is already here. Okay. So basically we're done with the loading portion. Save. Okay, just move to the analysis tab. Okay, before you hit this run analysis, this magic button, and we do need to check a few things. And one is design parameter. Okay, and for design parameters, we will check the resistance factor and losses right here, this one. And just want to make sure for this pre-stressing loss, we're using the correct value based on the relative humidity and climate. Okay, so if you click this relative humidity and this map pop up, just give you the relative humidity. And currently that we design things right here in the in this New York region. So the default 75, that is pretty accurate for this location. But if you design something that in the so in the dry region, like for example, Colorado, Texas, Arizona, and those, and you have to update the humidity in order to get the accurate number for the lump sum pre-stressing loss. Okay, so close that. The current value here, 75, match our location pretty well, so I don't change that. Just click OK. And for this computing loss using approximate method, okay, so it's default. And analysis factors, just try to double check for those that meet your design criteria like dynamic impact. And this program is actually automatically calculate live load distribution factor. And you can use your own calculation serve as a check, okay? But it's right here. Another thing that you can do some adjustment based on your particular bridge is the average daily traffic. Okay, so like this. And if you do have a very busy bridge, you do need to update that. Okay. So click OK. So other load factors are all like default in the AASHTO design code. Okay. And if you like do the permit vehicle, for example, you have to check strength 2 and make sure it's included. But for this example, we have only like HL93 level. It's already included as a default. Okay, so let's do the click OK. So like no modifiers. Like for this example, just leave as is as AASHTO design code. Okay, just click OK. So after we check design parameters, analysis factors, make sure those match your design criteria, and we can hit this run analysis button. And this program will automatically calculate the maximum moment, shear forces, and so on based on different state. Like you can choose strength 1 and take a look at the, at varying the reactions, the mid-span, so what is the maximum moment and so on. That's from this analysis. Okay. So after that, we will go to the beam design. So after you go to the beam design, so we first can highlight, okay, for example, the exterior girder and hit this strand pattern button. Okay, so this one show up, and we can do some of the strand design. And for usually that when we design strand, we need to refer to, okay, so we need to refer to um, the girder details specified by each state. For example, the New York state, the girder details, and we can take a look. Okay, so we can take a look of the details for the pattern of strand. Okay, so what we find here is like usually for this New York State girder line, the girder line, we have the spot for the straight strand. So the bottom layer here is 8, okay, maximum, and the second layer is 10 straight strand location, and third layer is 10, and the fourth layer is actually maximum 6. So let's take a look at the next page. Okay, so those are the locations for the pre-stressed strand. So make sure those, when you do the design, match those locations well. And we also take a look at the locations of the dripped strand right here. Seems that we can get maximum of 5 pairs. So total 10 strand for dripped strand. And the top two location is actually at least 8 inches from top of the girder to accommodate and other bars and so on. So the topmost dripped strand is 8 inches from top of the girder. Okay. For example, if we have a 54 inches girder, and the location of the topmost dripped strand should be 54 minus 8, so we get 46. Okay. And this also shows the maximum straight strand location. Here it is 8 for the bottom layer, second layer is 10, and third layer 10. Okay, so we will do that. Keep those in mind in design to match the state standard. Back to this. And before we do the manual input for the strand location, is like beneficial to do the auto design at the start. The auto design is definitely not your final design, but it's give you a good starting point. The current beam. Okay, click OK. So after you do design of the auto design, so this program just automatically pulls some locations of the strand and so on. So our goal is make sure everything on the right side here is black. Okay, so everything's okay for computed stresses as well as like a moment. So everything's okay here and no red spot for the initial stresses, final stresses, and so on. And we also need to make sure the camber deflection here, and as a minimum, that without live load, and this bridge should have upward deflection. And for this one, it's definitely doesn't meet the requirement. We have a downward negative number here showing the downward deflection of 1.33 inches. And for design, we do not want a sag curve for a typical bridge girders. And the ideal scenario is that after all the load applies, and we still have a positive or the upward camber for the entire bridge in order to make people feel safe driving under the bridge. So we try to avoid a sag curve for the girder line. Okay, so in order to increase, I say that's make the deflection work, we need to add more street strand. Okay, so to make sure those give you enough camber to accommodate the deflections due to the dead load and live load. And we also need to check the location strand like match the girder detail or not. And here we do see like 10 street strand at the bottom layer. So this doesn't meet the requirement. It should change to maximum number 8. Okay. After that, we do see some red spot. And the second layer on 10, that's okay. And third layer, let's see that we add more straight strand. See if that 10 work. Okay. So after you change some designs to 10, I do see a red spot here for the release stresses. And so if I check the deflection, so have improvement. Okay, so we already reduce the negative deflection to 0.11. Okay, so at this point, if you see some stress issue, and we have to add some drift strand. Okay, so the drift strand location currently for the auto design doesn't match the girder details. So we do need to change those. Okay, and for the drift strand, we can change to, based on the given information here, we can do like 5 pairs. Okay, 5 pairs. So if this is 46, this 44, 42, 40, and 38. Okay, so let's see if we use those spots. It is 38. Okay, this red spot gone. Okay, so red spot gone, and we do see increase, a little increase of deflection. Okay, so we change this drift strand, this drift strand location to 40 to match the girder detail. Okay, now this show up, and this one change to 42. Okay, and we do need to add more harp strand or drift strand in order to like remove those red spot. So here I do add a row and a drift strand and do 2. Okay, locate here is 2. So the location should be 44. And the middle height is above here. Okay, so should be this layer. The middle height should be 8. Okay, and 2 strand. Okay, so after you add more drift strand and this spot gone, and let's check the deflection. Okay, and for this deflection is already positive. Okay, it's already positive. So if you do want to like make like more benefit for the live load deflection, you can add. Okay, so you can like add more of the drift strand. Okay, or add 2 additional street strand and so on. So currently that this is okay for this location for exterior girder. I would say like try to copy this design to other girders. And for pre-stressing concrete girder, we definitely designed the exterior and interior girder exactly same in order to facilitate construction on the site, because it's impossible to tell the difference between the interior girder and exterior girder from outside. They all look same, so we want design the same. We try to copy the same strand design to our beams. Okay, so copy to our beams, click OK, and Okay. And you will visualize the strand pattern, okay, on the screen, and make sure the half strands are parallel each other, no intersections. Okay, so to make sure those are like parallel to each other. And we do want to check for interior girder if this pattern design work or not. Okay, so let's highlight the girder line tool and click strand pattern. Okay, so all the locations has a black number, which is good, but we do see a pretty large, okay, so pretty large, like a negative number for the deflections. For this scenario, okay, this scenario, you do have a like additional way, okay, to improve that. So one thing, okay, so one thing is you can put this, I would say that pre-stressing strength contribution in order to improve the moment inertia, or you can add more strength. For example, I put this. We do have a space for more pre-stressing strength. For example, that I do like add a row, okay, to straight. So do had like 8 and see that add 2 additional straight bar help or not. Okay, so this after that we do see that this number improved like 2.02. So this definitely is okay for now, but if you do want to make your design like completely positive here for the moment for deflections, I will say that click OK and um, back to this material. Remember that we actually leave these locations blank. And now, if you check this transform all pre-stressing tendons, make contribution to the moment inertia, check that. Okay, and go back to analysis. So you will see the change will affect that. Um, so we would just run analysis again and do the beam. Okay, and now you highlight this again for this check again this pattern. Everything black's good, and now you do see the deflection improve to positive number, which is very good. I would say that okay, since I changed the strand pattern for this example, I would like to copy that to other beams as well. Okay, so this our beam copy to other beam, click OK. Since we already assigned once, I will say yes to all. Okay, so click OK and double check the exterior girder and see the strand pattern still work for the exterior girders, everything black. And for let's see, it seems that there's some. Okay. Okay, so now this work. Okay, so this is showing the deflections of 0.8, 5, so positive number, pretty good. Everything look good for a strand design. So if you click the third one, double check. So this good, positive number, and so see that one, um, pretty good, and this one. Okay, so everything look pretty good for every girder. So basically this is your strand design. Okay, the next one is stirrup design. So after you do the strand pattern, next is rebar design, which is the stirrup to make sure the shear strands work. So hit this one. So I will use a typical interior girder as start rebar pattern. Okay, so this red line is the shear stress, the shear force demand. And we do need to design the stirrup, make sure the capacity, shear capacity above this red line. Okay. And for the stirrup design, so let's take a look at the standard design. Okay, so this is the detail for AASHTO. Look at this detail for the stirrups. Okay, and so we have the stirrup right here. So number 4 web stirrup bars, typical. Okay, so we have 2 legs in the web, 2 legs in the web, number 4. As well as for those stirrup, if you see the entire the stirrup shape is not only the web portion, is also have the outside those pieces to follow the exact same shape as the girder. And we do have this number 4 shear bars extend into the deck to make the girder composite with the concrete deck. So those are serve as like shear connectors extend into the deck, which is number 4, epoxy coated. So this E represents epoxy coated or G represents galvanized. And stirrup spacing. Okay, so this is the typical pre-stressed concrete girder stirrup spacing. And we try this first. If it doesn't work, we will make some adjustment to improve the shear strength. But as a start, and we will try 6 spaces at 3 inches from the girder end. Okay, and then another 6 spaces, 4 inches, and 6 spaces at 6 inches, and 6 spaces at 9 inches. And after that, the remaining of the length of girder, we will use the minimum 12 inches stirrup spacing throughout the entire girder, in addition to those end zone, okay, the end zone. So those are due to the demand. You will see the shear demand is pretty high at the girder end, and then it's relatively low throughout the entire girders in the middle portion. Okay, so let's do that. For number of legs, 2, and size is number 4, pretty standard. And stirrup spacing 3 inches, extend to deck, yes, starting from 0 and end as 1.5. Okay, so this represents 6 spaces. And after that, we can do the copy. Okay, so do the copy. So we can change the spacing to 4 and start positions 1.5 and to 3.5. So all of those should match those input. Okay, so this is a typical girder spacing starting point and end point. Okay, so now it's 6 inches from 3.5 to 6. Okay, so we can do this like 2 legs, number 4, spacing 6, and start 3.5 and end at 6.5. Okay, then another row, 2 9 inches, and start from 6.5 to 11. Okay, you do see the green lines here. So our goal is the green lines above the red line to show the shear capacity greater than the shear force. Okay, so another row, 2 12 inches, okay, and from 11. And instead of manually input the end feet right here, we actually make this design symmetrical for the entire girder. So this button makes symmetrical and click OK. So it's automatically designed the stirrup designs symmetrical, and I'll automatically calculate those end location for each stirrup design. Okay, so now we see this every portion, the green color lines above the red color line means that capacity meet the requirement. Okay, and I will do this copy to after I fill this happy and copy to all beams for the stirrup design and click OK. So after that, you will see those stirrup spacing on the girder elevation. Okay, um, and I will double check the exterior girder design rebar pattern. So make sure exterior girders also meet the requirement of those the green line above the red line. Okay, so everything's good. I just save the project. Okay, so at this point, we already designed the strand pattern as well as the stirrup size and spacing. We're done with the entire bridge design. And you can do some of the check here and take a look at the design. For example, strand 1, and let's take a look at the ultimate moment for composite moment. Okay, composite moment. Okay, composite moment for the green line represents the capacity and the red line represents the okay. So this give you the live load moment. Um, you can change the girder line and just take a look at the moment demand for across the entire girder line, things like that. Okay. And you can click the results and just give you some output of the maximum and the shear force and so on. So you can change the strength 1 to give you those output. Okay. If you click the images, you can see some renderings of the superstructure. Okay, so I think that we're done with this example, and that's it.